Hello everyone, I am Rahul from Department of Chemical Engineering IIT Bombay, and I am conducting this session to solve the previous year GATE questions of Chemical Engineering Department. And right now we are looking into the questions from heat transfer subject. So we will wait for a couple of minutes more and then we can start the session. I think I can start the session now. Again, good evening, everyone. So, today we are solving the questions of heat transfer subject from GATE 2020 paper. And yes, the first question is this as shown on your screen. So basically, we are given a hollow cylinder of the given dimensions, and we have been asked to find the view factor. So does anyone of you know what a view factor is in the audience? What is a radiation view factor? Okay, so I will start the video solutions, and meanwhile relevant the course material related to this question can be found out in this link. So here you will find out what is a view factor and what are the basic laws that you need to solve these questions. So basically you need to remember this additivity rule and reciprocity rule to solve the questions related to this view factor. So when I say additivity rule, it means that summation of Fij will be always equal to 1. That is F11 plus F12 plus F13 dash dash F1n will be equal to 1, where F11 is the radiation of energy emitted by surface 1, which is again incident on surface 1. Similarly, 1,2 can be defined as radiation of the amount of energy leaving surface A1 and which reaches surface A2. That will be F12. So in this question, we have been asked to find F21. So that is basically amount the radiation energy leaving surface A2 and reaching surface 1. So basically the amount of energy that is leaving from this surface, the inner surface, and which reaches this top surface A1. So that we have been asked to find. And we are provided with this F13. So let's look at the video solution of this question. Let me know if the video or I am not audible. Hello everyone. We will be solving question 35 of GATE 2022, GATE 2020 chemical engineering paper, and the subject is heat transfer. The question is a hollow cylinder of equal length and inner diameter, that is L equal to D, is sealed at both ends with flat plate as shown in figure. Its inner surfaces A1, A2 and A3 radiate energy. Fij denotes the fraction of radiation energy leaving the surface Ai which reaches the surface Aj. It is also known that F13 is equal to 3 minus of 2 under root of 2. Which one of the following is correct? So we have been given 4 options corresponding to F21 and we have been asked to find its value. So here we shall use the concept related to radiation view factor to find the radiation that leaves surface 2 and reaches the surface I. Okay. So how do we define view factor as? So in order to find the radiative heat exchange between two bodies, the view factor is defined as F12 is the fraction of energy leaving surface 1 which reaches surface 2, and F21 is vice versa. Similarly, in general terms, we can denote Fmn as fraction of energy leaving surface M which reaches surface N. Okay, so let's say if I'm having the two surface over here. And in both this case, the inner side is my reflecting one. I will call this the surface 1, this is surface 2. Then F12 will be the fraction of energy that leaves surface 1 and reaches surface 2. This is my F12. This is my F21. Okay, because this will be incident on first surface and similarly this will be incident on second surface. Similarly, F11 will be the fraction of energy which leaves surface 1 and reaches again to surface 1, and in this case F11 will be equal to 0. Similarly F22 equal to 0. Okay, so few more concepts related to that. So this one is known as reciprocity theorem. So what it tells is, if the area of surface 1 is A1 and the fraction of energy leaving surface 1 and reaching surface 2 will be F12, then we can also write this as A1 F12 is equal to A2 F21. So this can be generalized. So basically this is derived according to this law. So if the energy leaving surface 1 and arriving surface 2 is given by this term, and the energy leaving surface 2 and arriving surface 1 is given by this term, then all the incident radiation will be absorbed by black body, and the net energy exchange will be given by this. At thermal equilibrium, Q will be equal to 0, and the energy emitted by both this black body will be equal. So we can equate that to 0 and we can get this reciprocate theorem. Also, then there is this relation between the two factors that we need to remember. You can also call this as additivity rule. So what this says is summation of j equal to 1 to n. That's for all the surfaces f. The summation of fij is equal to 1. So if I'm having two surfaces, then f11 plus f21 will be equal to 1. So this we can write, and now we will be using this reciprocity theorem as well as additivity rule to solve the question. So here we have been given a hollow cylinder of equal length and inner diameter. So let's just write it over here. L is equal to D, and A1, A2, A3 are the inner surfaces and they radiate energy. And we have been given F13 is equal to 3 minus 2 root 2, and we had to find F21. Okay, in all these cases we have to find F21 and just compare the values, which one of the following option is correct. So F21 is question mark. Okay, so for this surface, from the additivity rule we can write F11 plus F12 plus F13 will be equal to 1. Now we can say that the energy that will leave from surface 1, that is F1, it won't ever reach this again the surface, because this is a flat surface. If it would have been curved surface, then the radiation leaving one might reach surface 1 again, but not in this case, since we are having a flat surface. So F11 in this case will be equal to 0. Okay, so we can just replace it over there, plus F12 is equal to 1 minus F13. We have this value of F13 from here, so we will just put it over there. So it will give us minus 2 plus 2 root 2. So we have the value of F12, but we have to find the value of F21. So now we can use the reciprocity theorem over here. So that is given as A1 F12 is equal to A2 F21. Now let's just find the area of A1 and A2. Okay. So A1 will be given as pi r square. So that we can write this pi d square by 4. Similarly, A2 is this surface, the curved surface. So it can be written as pi d into L. Here, since L is equal to D, we can write this as pi d square. So we will just replace the values of these two areas in this equation, and we can get This pi d square will get cancelled. So we will be having the value of f12 is equal to f12 is 4 times of, no, we have to find f21, so f21 is equal to f12 upon 4, and f12 we will use from this equation, so it will be minus 2 plus 2 root 2 upon 4. So you can simplify this as root 2 minus 1, 2 will cancel. So this is our final answer, root 2 minus 1 upon 2. So yes, in this question we looked upon the basic concept related to view factor, and we found out that the view factor f21 is given as root 2 minus 1 by 2, and from the given option we can select that only one of the following will be correct, that is the option B. So if anyone has doubt, then they can speak up or write in the chat box and I can solve that, or else we can wait for a couple of minutes and then I can move on to next question. Do you have any doubts regarding this question or the concept related to view factor? Okay, so I'll just repeat that. So let's say I'm having two surfaces. This is my first surface, and this is my second surface. In both the surface, this inner side is the reflecting one. So if I consider this first surface, then I can, according to this, wait a minute, you asked which, then according to the additivity rule for this first surface, you can write f11 plus f12 is equal to 1. Similarly, for second surface, you can write f21 plus f22 is equal to 1. This you can write from the additivity rule. Similarly, if there are more than one surfaces, then for each of these surfaces, I can write that summation of Fij is equal to 1 for j is equal to 1 to n. So this is my additivity rule. I hope that clears your doubt. Okay. So let's look at the second question. So in this question, we have been given that a fluid is heated from 40 degrees Celsius to 60 degrees Celsius in a counter current double pipe heat exchanger. Hot fluid enters at 100 degrees Celsius and exits at 70 degrees Celsius. The log mean temperature difference, that is LMTD in degrees Celsius, is dash. So we have to find this log mean temperature difference for a double pipe heat exchanger. This concept related to LMTD has been asked in almost almost all the sessions that we have conducted over the past few weeks. So this is a very important concept related to an LMTD. The formula is simple and we just need to put the values and find the log mean temperature difference. Okay. So let's just quickly see the video solution. This will be a short question. Hello everyone. We will be solving question 41 of GATE 2020 chemical engineering paper, and the subject is heat transfer. The question is, a fluid is heated from 40 degrees Celsius to 60 degrees Celsius in a counter current double pipe heat exchanger. A hot fluid enters at 100 degrees Celsius and exits at 70 degrees Celsius. The log mean temperature difference, that is LMTD, in degrees Celsius is dash, round off to 2 decimal places. The relevant course materials can be found out in this given link. So in this question, we have been given a double pipe heat exchanger. Let's just draw a general schematic of a double pipe heat exchanger. And hot fluid enters at 100 degrees Celsius and exits at 70 degrees Celsius. Okay, so let's just write TH in, and this is TH out. And cold fluid is from 40 to 60. And here we have been given counter current. So the direction of the flow of both this hot fluid and cold fluid will be opposite. So this will be TC in, this is TC out. So we can also draw temperature profile across X. So the hot fluid, we can just draw temperature profile as this. This is my hot fluid and it goes from 170 degrees Celsius. Similarly, the cold fluid will go from 40 to 60 degrees Celsius and the temperature will increase. So this is 60, this is 40, and this is my flow. And this is for counter current flow. If we had co-current flow, then the direction would have reversed, and in that case it should have been 100 to 70, and this will be 60 to 40. Yes. But here we have been given counter current, so we will be using this temperature profile. And LMTD, the log mean temperature difference, is given as delta L is equal to delta T1 minus delta T2 upon ln of delta T1 upon delta T2. So we will be using this temperature profile and not this one. So here we can, this temperature difference is known as, is defined as delta T1, and this we can write it as delta T2. So delta T1 is 40 minus delta T2 is 70 minus 40 is 30 upon ln of again 40 upon 30. This we can write it as, so we can solve this and we will get delta TL as 34.776 degrees Celsius. So this is our log mean temperature difference based on counter current double pipe heat exchanger. So this was a numerical answer type and we have to write the answer till 2 decimal places. So we will report the answer as 34.76. Okay, so this was a straightforward question. In the video, I just made an error in this direction. So in this case, the direction as the fluid is heated from 40 to 60 in counter current. So direction will be opposite of to that of the hot fluid. Rest all the calculations were correct, and I guess you have also solved correctly. And the final delta T was 34.76. So we can move on to the next question. So in this question, it is related to this extended surface of fins, and we have been asked to find the temperature at a distance of x equal to 25 centimeter from the base for this rectangular fin. Okay, so let's look at the video solution. Hello everyone. We will be solving question number 42 of GATE 2020 Chemical Engineering paper. The question is, consider an infinitely long rectangular fin exposed to a surrounding fluid at a constant temperature Ta equal to 27 degrees Celsius. The steady state one-dimensional energy balance on an element of film of thickness dx at distance x from its base yields this equation, where theta is given as Tx minus Ta, where Tx is the temperature of fin at distance x from its base in degrees Celsius. The value of m is 0.04 centimeter inverse, and the temperature at the base is T0 equal to 227 degrees Celsius. The temperature in degrees Celsius at x equal to 25 centimeter is given as. So here we have been asked to find the temperature across fin where when x is equal to 25 degrees Celsius. Yes, so here we have been given as Ta is 27 degrees Celsius and T0 is 227 degrees Celsius. From here this is 27 degrees Celsius and this is 227 degrees Celsius, and we have been asked to find that at x equal to 25 centimeter what is temperature. So first we will use this equation to find the temperature profile across the fin. Okay, so this is a second order differential equation, and we know that the roots of this equation of the form of this d square theta is equal to m square theta will be plus or minus m. So we can write that as roots of this auxiliary equation lambda will be equal to plus or minus of m, and the general solution of the equation will be theta is equal to c1 e raised to mx plus c2 e raised to minus mx, where theta is given as Tx minus Ta. We will just replace it here. Now we need to find the values of this constant C1 and C2 so that we can get the temperature profile by using the given conditions. So the first condition that we have been given is, first we have been given that consider an infinitely long rectangular fin exposed to a surrounding fluid at a constant temperature of Ta is equal to 27 degrees Celsius. Okay, so we can write that as, let's say, at x equal to 0, the temperature is given as T is equal to 227 degrees Celsius. So this we can write it from here. So we will replace this value in this equation and we can get it as 227 minus Ta is equal to C1 e raised to m into 0 plus C2 e raised to minus m into 0. So this will be equal to 227 minus Ta is equal to C1 plus C2. Similarly, we can write that as at x equal to infinity, the temperature will the fin will become uniformly, temperature distribution will become uniform at time equal to infinity, so that we can write the at x equal to infinity the temperature will become 27 degrees Celsius. So this we can write it as 27 minus Ta is equal to C1 e raised to m into infinity plus C2 e raised to m into minus of infinity. So Ta also we have been given as 27 degrees Celsius over here, so this will become 0 is equal to C1 e raised to m into infinity, and this will become C2, so this term will become 0. So from there we can write that 0 is equal to C1 into e raised to infinity. We know that this value will be very large value, that is infinity, so C1 only will be equal to 0. So that implies C1 is equal to 0. And from the earlier equation, we had C1 plus C2 is equal to 227 minus Ta. So we'll put C1 is equal to 0 over here. C1 plus C2 was equal to 227 minus Ta, and this is equal to 0. So C2 is equal to 227 minus, we also have the value of Ta, that is 27. So this will, C2 will become 200. Okay, so now we will put the values of C1 and C2 in our temperature difference equation. So this is Tx minus Ta is equal to C1. C1 we found it as 0. So 0 plus 200 into e raised to minus mx. So Tx, Ta 27 upon 200 is equal to e raised to minus mx. Now we have been asked to find the value of temperature at x equal to 25 degrees Celsius. So we will just replace the value of x over there. The value of m we have been given as 0.04. X is 25. So this we can simplify as T of 25 minus 27 is equal to, this term will be equal to 0.367 into 200 . So yes, the temperature at x equal to 25 centimeter will be equal to 100.57 degrees Celsius. So yes, we can write the final answer as 100.57 since this was a numerical answer type question. Okay, so if anyone has any doubt, then they can write in chat box related to this question. In this question, we derived this temperature profile for a rectangular fin of infinite length and then solved for x equal to 25 centimeter to find the temperature. If you have any doubt, then you can ask, or else we can move to the next question. Okay, so let's move on to the last question of today's session. So in this question, we have been given a double effect forward feed evaporator, and then there are these flow rates and the temperature of the exit stream from first and second effect, and we have been asked to find the steam economy. Let's look at the video solution. Hello everyone. We will be looking at question 45 of GATE 2020 chemical engineering paper. The question is, an aqueous suspension at 60 degrees Celsius is fed to the first effect of a double effect forward feed evaporator with a mass flow rate of 1.25 kg per second. The sum of the rates of water evaporated from the first and second effect is 1 kg per second. Temperature of the exit streams from the first and the second effects are 100 degrees Celsius and 60 degrees Celsius respectively. Consider the specific heat of the aqueous suspension and the latent heat of phase change for water to be 4 kJ per kg per Kelvin and 2200 kJ per Kelvin respectively over this temperature range. The steam economy in kg per kg is given by round up to 2 decimal places. So in this question, we have been given a double effect forward feed evaporator and we have been asked to find the steam economy. So in general, any double effect evaporator is given by this general schematic. So we have this feed, which is basically an aqueous solution that needs to be concentrated, and we provide steam as a heating medium, which is used to evaporate the solvent or water that is present in this feed, so that it can be so this steam basically evaporates the solvent or water present in the feed to concentrate it. Yes, so in the first effect, the concentrated solution will be again fed as an input to the second effect, and similarly the vapors that have been generated in the first effect are used as a heating medium in the second effect. So yes, practically this steam and condensates are removed from the evaporator, but for our purpose, for energy and mass balance, we will be neglecting these two streams. So now from the given question, we have been given that the aqueous suspension is fed at 60 degrees Celsius. So here the temperature of the feed we have been given as 60 degrees Celsius with the mass flow rate of 1.25 kg per second. So let's just write m dot f as 1.25 kg per second. And the sum of water evaporated from first and second effect is 1 kg per second. The temperature of the exit stream from the first and second effects are 100 degrees Celsius and 60 degrees Celsius. So in the first effect, we have been given the temperature as 100, the temperature will be 100 degrees Celsius, and in the second effect, the temperature will be 60 degrees Celsius. So both the outlet will be at the same temperature of 100 degrees Celsius and 60 degrees Celsius. So here also temperature will be 60 degrees, 100 degrees Celsius. Here it will be 60 degrees Celsius. Similarly, here it will be 100 degrees Celsius, and the final product will get out at 60 degrees Celsius. And we have been given this specific heat and latent heat for phase change. So let's just consider if the mass flow rate of the steam is m dot s, the vapor generated in the first effect is V1, in the second effect the vapor generated is V2. The liquid obtains are concentrated liquid obtains are L1 and L2. So for such a case, we define steam economy as kg of vapor obtained upon the kg of steam that has been used to vaporize the kg of steam that has been used to generate those vapor. So that we can write as kg vapor upon kg steam used. So in this case, the vapor generated will be V1 plus V2. And the steam we have considered as m dot s. So the steam economy, we have to find these three terms. So for that, we will be writing mass balance and energy balance across both of these evaporator individually and then equating them to find the desired values. So let's just start with mass balance. So for this first first evaporator, we can write that the feed is equal to vapor plus L1. So that we can write it as feed, we are writing it as F is equal to L1 plus V1 for this first. Similarly for second effective evaporator, now my L1 will become the input. So L1 will be equal to V2 plus L2. Now we can replace this value of L1 in this mass balance for evaporator 1, and we can obtain V2 plus L2 plus V1 is equal to plus L2. Now in the question we have been given that the sum of the rates of water evaporated from the first and second effect is 1 kg per second. That is V1 plus V2 is equal to 1, that we have been given. So we will just replace it over here and we can get F is equal to 1 plus L2. Okay, so we will be using all this equation to find the steam economy later on. So now we have done the mass balance. So now we will write the energy balance for the same system. So for the first first evaporator, we can write energy balance as okay. So Q can be written as, we can write it as enthalpy of the steam. Okay. So the mass flow rate was m dot s. So we can write it as m dot s into lambda s is equal to this. Basically, the steam will be used to change the temperature of the feed. Okay, so basically this will be liquid, and so if this is F, this is L1, V1, V2, and L2. So the temperature of this liquid stream F will be changed. Similarly, this steam will be used to vaporize this liquid. Okay, so that we can write it as enthalpy of liquid plus vapor, mass flow rate of feed to Cp of feed into the temperature change of the feed will be, so the inlet temperature was 100 degrees Celsius. No, the inlet temperature was 60 degrees Celsius, and in the first effect we had this 100 degrees Celsius. So the enthalpy across here was 100 minus 60, plus we have to write the enthalpy of vapor. So the vapor that will be generated is V1. So this V1 we can write. So usually it is written as m dot f minus this. This is the mass of the liquid into lambda V. Okay, and this term is equal to this vapor. So basically we can write this as lambda s. We have been given it as latent heat of phase change of water as 2200 kilojoule per kg. So this is 2200 into mass of steam we don't know. The mass of the feed we have been given as 1.25. It is over here. Similarly, the specific heat of aqueous suspension is 4 into 40 is plus. Now this, the amount of vapor generated is V1. So this is V1 into lambda V is again 2200. Okay, so we can simplify this equation and write it as 2200 into m dot s minus v1 is equal to 1.25 into 4 is 5, 5 into 40 is 200. So we have this after writing the energy balance over first system. Similarly, we can write the energy balance over second evaporator. So in the second evaporator, this V1 will be used to heat my system. Okay, so that we can write it as Q is equal to V1 into lambda 1 is equal to, now the feed rate will be at the outlet of this first evaporator, and that will be L1. So, and the temperature over here was 100 degrees Celsius, and over here it is 60 degrees Celsius. So that we can write it as L1 into Cp into, now the temperature difference will be 60 minus 100. So that we can write it as 60 minus 100 plus, we had this was for liquid, and now we have to write it for vapor. So for vapor generated here will be V2 into, we can write it as lambda. Okay, so now we can just replace the value. V1 into 2200 is equal to L1 into the specific heat of this suspension is given as 4, so that we can write it as L1 into 4 into minus 40 plus V2 into lambda V is 2200. We can write this as V1 V2 to 2200 is equal to, now we know that V1 plus V2 is equal to 1. So that will give V2 is equal to 1 minus V1. So this we will replace in our equation. It will become V1 minus of 1 minus V1. So this will become 2V1 minus 1 to 2200 is equal to minus of 160 into L1. Now L1 we don't know as of now, but we have the value of feed. So from that, F is equal to L1 plus V1. So from that we can write L1 as, so let's just write it over here. F is equal to L1 plus V1. So L1 will be equal to F minus of V1. So that we can write it here as F minus V1, and we have the value of F as 1.25 minus of V1. So we can write this as 4400 V1 minus of 2200 is equal to minus of 200 plus 160 V1. So from here we can solve for V1. So V1 will become 2000 upon 240. So V1 will become 0.4716. Okay, so we have the value of V1 as 0.4716. Now we We can put that value of V1 over here. To find the value of m dot s. So m dot s will be 200 upon 2200 plus 0.4716. So this will, so the mass flow rate of steam will come somewhere around as 0.5625. So now we have this value of m dot s, and we also have this v1 plus vt equal to 1, and then we can find the steam. We can write the steam economy as v1 plus v2 upon m dot of s, that is 1 upon 0.5625, and it will become 1.77. So this is my steam economy, and from the answer also we can write it up to 2 decimal places. The final answer, that is steam economy in kg per kg, as 1.77. Okay, so we looked upon this question of heat transfer, and the main thing to remember in this are these energy balances. How you do this energy balance over this first evaporator and second effect evaporator, that is the main thing of concern. So you can just remember this equation and then just use them straightforward to find the steam economy or the energy balance. If you have any doubts in this question, then you can ask. This is the last question, and we will be ending the session after this. I will just wait for 5 minutes. If you have any doubts, you can ask, or else we can end the call for today. So yes. If you don't have any doubt, then we can end today's call. Next time also we will be solving the questions from GATE 2019 heat transfer paper. Okay, thank you everyone for attending the call. I think I can end the meeting now.